Ladies and gentlemen, I am Ling from South China University of Technology, and it's my pleasure to give a presentation on our recent stories about application of salt hydrate expanded graphite composites with thermochemical storage in mitigating battery thermal runaways. It's a study with both experiment and simulation. And my presentation includes the following four parts. The first one is the background, and we have seen a lot of accidents caused by the lithium-ion batteries in recent years. Whether about the Tesla, NIO, the electric vehicles, or even some from the lithium-ion battery recycling factory, or some electric bicycles, and these accidents are caused by the thermal runaways of lithium-ion batteries, and because lithium-ion batteries are really temperature sensitive energy device. If the batteries are encountering problems of overheating, they could get in fire or explode. And so the battery really needs a system for about the thermal management. And we have a lot of methods we can control the temperature of batteries, including the air cooling, the liquid cooling, and also we have a choice of PCM cooling, the phase change materials. I noticed that in the next two lectures, we can see that Dr. R. Halash will give about a new lecture. He actually firstly proposed the PCM-based cooling systems. PCM cooling systems is actually a system that uses the PCM, which is a material that can store a large amount of heat during a solid to liquid phase transition. For example, when ice melts into water, they absorb a lot of heat inside it. We take it as the latent heat. For example, the 1 kilograms ice can absorb 334 kilojoules heat, which is larger than its specific heat, which we calls it the sensible heat, which is only about 4.2 kilojoules. So if we use PCMs to cool down the battery, we can use the very large latent heat to cool it down and maintain the temperature with the constant temperature. We call it the phase change temperature. However, if we use the PCM for protecting the battery from thermal runaways, the PCM actually is not a very suitable choice. There are two reasons. The first reason is that most lithium-ion battery, they are triggered to thermal runaways at a temperature above 120 degrees C. At the temperature or above, the separators inside the batteries starts to melt, and the internal short circuit could be triggered, and then the thermal runaways are happening. And during this process, the heat density of the battery is very high. When a battery is encountering thermal runaways, it could release about a heat larger than 800 joule per grams of the battery. In most PCMs we used for battery thermal management systems, we found that most of them are paraffin. We can see from these figures in the right figure, most are the paraffin, and they are flammable. So the PCMs, when the PCM itself getting fires, it could making the cases worse when the battery is encountering thermal runaways. And in another aspect, most PCMs melt at a low temperature, and most of them have a melting point below 60 degrees C, which is unmatched with the thermal runaway temperature of the battery. And third, most of the PCM, their energy storage, thermal storage density is limited below 250 kilojoule per kilogram. So it is also much lower than the heat density of the battery. Based on these conditions, we can conclude that the PCMs we use now are mostly neither safe nor efficient to prevent battery from thermal runaways. And so we here propose a new strategy. We want to introduce the inorganic salt hydrate with the two-stage thermal storage. So we explained what is two-stage thermal storage. The first stage, the salt hydrate could have a solid to liquid phase change as the other PCMs do. In these cases, in this stage, it melts at a temperature about 50 degrees C, with the melting enthalpy about 250 kilojoules per kilogram. What's more of the PCM than what's more of the salt hydrate than the other PCM is that he has a thermochemical reaction at a temperature above 100 degrees C, with the with the energy density about 650 kilojoules per kilograms. So with this salt hydrate, we can use it to cool down the battery when they are operating normally, or we use the thermochemical storage to protect the battery from thermal runaways when the temperature reaches above 120 degrees C. So we use one material, just one, to solve the two problems of lithium-ion battery in cooling. And in this study, we prepares a multi-scale encapsulated the sodium acetate trihydrate urea. We call it SAT urea. We use an expanded graphite matrix to absorb the SAT urea eutectic into the micro pores inside it. It's a micro scale encapsulation strategy, and on the surface we also use an organosilicon sealant as a micro encapsulation strategy. With this two scale encapsulation strategy, we can enhance the stability of the salt hydrate, and this salt hydrate composite is then applied to a battery thermal management system. After that, we also tested protection effects for the battery that come into the problems of thermal runaways. In these tests, we use some dummy cells with the heater instead of real battery cells, because it's a little bit dangerous to use the real cells. So we use some dummy cells to simulate the battery that come into thermal runaways. We tested the protection effects in a single cell or in multiple cell module. And the following are the results. First, the thermal properties of the set area EG. We can see from the differential scanning calorimeter analysis here, we can clearly see that with the set area, we have two endothermic peak. The first one is about 48 degrees C, and the second one is about 118 degrees C. And the first one, in the first peak, it indicates the latent heat of the salt hydrate reaches 181 joule per grams, and the second one indicates it has a thermochemical storage density about 567 joule per grams, which matches the magnitude of the heat generated during the battery operating normally or encountering the problems of thermal runaways. And the mechanisms of the thermochemical storage SAT urea we also characterize it with TGA, and we can see that when it melts, the water molecules remain inside the salt hydrate. However, when the temperature is above 100 degrees C, the water evaporates, and that provides an extra thermal storage than the PCM. And we also test the fire resistance effects of the salt hydrate and compare it with the organic paraffin EG. From the figure in the left, we can see that if we move a fire source, put a fire source away, move the fire source away from the salt hydrate, the set area, we can see that the fire stops. However, in the cases of the organic paraffins, even we move the fire source away, the paraffin EG continues. The fire continues. So we can conclude that the inorganic PCM is safer, and we also use the PCM to cool down the battery when they operate normally. We can see that the battery temperature can be controlled within 52.3 degrees C, with the maximum temperature difference less than 4.0 degrees C. So it's a good material to cool down the battery. And in the thermal runaways cases, we can see that compared with the paraffin, the salt hydrate could reduce the battery temperature from 400 degrees C to less than 250 degrees C. The temperature is lower than the paraffin cases because it has thermochemical storage plateaus. Here we can see that, and in multiple cell module, with the salt hydrate, it can also